I think what's missing in our theories are the big connections that hold the entire universe together. So it's kind of at the exact opposite end. I don't think that the big mysteries that we have left to solve are on the tiny scales, but they're on the large scales. They concern how we are embedded in this entire universe.
Welcome to Closer to Truth. I'm speaking with Sabine Hossenfelder about her new book, Existential Physics, A Scientist's Guide to Life's Biggest Questions. It's a terrific read. I can't wait to discuss it. Sabine is a theoretical physicist working in the foundations of physics, from cosmology to quantum foundations and particle physics. She's a writer and an author and a content creator for her popular YouTube channel, Science Without the Gobbledygook, where she summarizes latest science, debunks myths, and offers, shall we say, strong opinions. At last check, Sabine had 487,000 subscribers, and Closer to Truth has 481,000 subscribers. So, Sabine, we look up to you. It's great to see you again. Congratulations on the book.
Good to see you.
Closer to Truth, as you know, also focuses on the biggest questions. So one of my themes is I want to be comparing our biggest questions. Forget about the answers. I want to know if we're asking the same kind of questions. And I'd like to start just by asking you about how you selected the biggest questions. Chapter by chapter, you have each one. What motivates these biggest questions of yours?
Well, that was actually pretty easy. I just looked at all the stuff that I talked about before and that I'd written about before and asked myself what were most people interested in. And it just struck me that the stuff that people were interested in were stuff about how did the universe begin, what is time, how can we make sense of space, are there copies of us in other universes? It was all those big existential questions. And then I thought, well, I think I would just connect them and make a book of it.
That's great. And I noticed that you included 4 other voices, people you interviewed, which I thought was an unusual feature, but a very good one. What motivated that?
Well, as you correctly said, I have very strong opinions, and I didn't just want people to hear my opinion. I also wanted them to hear what other people think, physicists, but also with Zia Merali, science writers.
Yeah, and I thought that was a great feature, and the way you handled it was very good. One got a sense of the interview process and the personalities involved, so that was great fun. Let's dig right in and start with chapter 1. Does the past still exist? And we know this is the old tension between the block universe that Einstein pioneered and versus presentism, that the only real thing is the present time. We understand the alternatives. Where do you take your stand?
I'm trying to look at what we can really tell from physics, and I think my whole book is like this. It's like I phrased it very carefully, like this is how much we know, and then you can interpret it this way, and this is what I think. And it's the same with this first chapter. So I think we are very confident that general relativity is pretty much correct, up to those minor issues with quantum gravity. And it gives us a very specific picture of time. And I think we have to take this seriously.
So one of the tensions between quantum mechanics and general relativity is how each deals with the nature of time. So are you giving preference to the general relativity's approach, which leads to the block universe?
Well, I think the block universe is just something that follows from general relativity. And then you lump quantum mechanics on top of that, and you have to reassess some of those questions. And in quantum mechanics, the way that we presently use it, we still have a deterministic evolution to the moment of measurement. So I think when you're talking about the past, it doesn't really change anything. It's a deterministic evolution. You can put your block universe there. When it comes to the future, it's more difficult because in quantum mechanics, the future has this random element that comes in from the measurement process, which is why in my book I mostly talk about the past. Do we know that the past still exists? So personally, I don't think the measurement process is fundamental. I think it's just an approximation to what really goes on. And in this case, the underlying true evolution would still be deterministic. So I think the block universe survives.
And it does because you are taking a very specific view of quantum mechanics in terms of whether it's hidden variables or stuff going on underneath, which ultimately, so you're a real Einsteinian in your approach, I think. Would that be fair?
Well, if you're asking about my research, yes. But in the book, I'm basically trying to tell the story about what we know, right? So this is what we know, general relativity, and then there's quantum mechanics, and then there's this issue with the measurement in quantum mechanics, which we don't understand. So how much can we really say? Well, I think we can reliably talk about the past. And then when it comes to the future, we don't really know.
Look, that's a fair comment, and I appreciate that about the book, that you say over and over again where you have confidence that we know, and where people, many things that you talk about, whether religion or multi-universe, the multiverse, you put in the same category. You can believe it if you like, and I can't prove you wrong. But it's ascientific in the sense that it is not a question that science can answer. So you do that very well, and I appreciate that. But I also like to dig a little deeper and find out where you think you stand yourself. So I think it's very clear with general relativity and quantum mechanics where you stand, and that's good. Another feature of that chapter which I liked was the concept of when information is preserved, in a sense that all lives, in some sense, you have a grandmother story, are immortal because information is not destroyed. So all of this is, are you trying to give people kind of a little bit of a hope that there is some kind of a physics founded afterlife? Because I would think it's more of a mathematical formalism than a kind of a real approach to some kind of an immortality.
Well, yeah, immortality would be putting it a little too strongly, but it's certainly true. If you believe that the time evolution of the universe is reversible, then information can't really get lost. It can't be destroyed, because you can always, from the present state, whatever time that is, you can always reconstruct the initial state. And I actually think it's a very spiritual insight that follows from our understanding of the laws of nature that we don't really emphasize enough. I think it's a really deep point. And yeah, I mean, I'm definitely trying to give people some hope, as you put it, though that's maybe not a word that I would have chosen, some inspiration maybe.
When I was reading that, I was trying to articulate that with the approach to immortality in the Abrahamic religions, which is immortality of the soul or an afterlife or a resurrection, and in Eastern religions of the so-called merging of the dewdrop of our consciousness into the great ocean of cosmic consciousness. In both of those images, you can see a little articulation with what you're talking about. Is that fair?
I think it's easier to see in the latter, like this merging with the cosmos in some sense, whether you want to believe it's conscious or not. I think you definitely have this. I mean, it's undeniably true that when we die, then the information that is contained in the structure of our body decays. Like it goes away, it spreads out through the universe in some sense. So we become part of the universe. So I think that's pretty safe thing to say. Now, if you're talking about something like a soul, depends on what you mean by it, right? You could say, well, I want to interpret the soul as the essence of this information. And in this sense, it is preserved.
Mm. Okay, I'm not sure that gives me either hope or inspiration, but it's certainly a new approach to kind of a spirituality that physics perhaps can give us. Second chapter is on the universe, the beginnings and endings. We love the questions, and your approach basically is to discuss many of the theories that we all talk about and kind of dismiss all of them as scientifically limited, and that you can believe it if you like, but there is no scientific basis for anything in terms of at least the beginning of the universe. I'm not sure the end. And then you focus on the initial conditions, that each one has a very specific kind of initial conditions that were unique in that case. And you say you'd like a theory that does not need special initial conditions. So how would that work?
The problem that we have when we talk about the beginning of the universe is that all the theories which we currently use in the foundations of physics work the same way. We have something that's called an initial state, which describes whatever it is that you're talking about, in this case, the entire universe, at one moment in time. And then we have an equation that we can use to calculate what happens at any other moment. So when we're talking about the entire universe, we're starting with this initial state somewhere at an early time, and then we calculate how the universe evolves after this, structures form, galaxies, galaxy clusters, us at some point. So that's how it currently works. But this approach, when you're talking about the entire universe, has some fundamental limitations, which is that this initial state has to be simple, because otherwise it doesn't explain anything. Like if you take an arbitrarily complicated state, you can't calculate anything with it. So it's not really a scientific theory. And the problem which follows from this is that if you are inventing, let me put it this way, a theory for the beginning of the universe, which is in some sense unnecessarily complicated, like you're inventing an earlier phase of the universe, like you have in a cyclic universe, or you're inventing some story about collisions of higher dimensional membranes, or you come out of a higher dimensional black hole, or string gas, or stuff like this. This is all unnecessary to describe what we observe. And therefore, I think it's not actually scientific. It's ascientific. You can believe in it if you want to, but there's no evidence that actually speaks for or against it.
I might argue that one can differentiate between some of the theories, the collision of membranes, ekpyrotic universe, or conformal, has a lot of interesting ideas, but really no evidence. But inflation theory, the argument is that there are at least evidence, whether the cosmic microwave background or other, that is consistent with inflation theory.
Oh, yeah, sure, it's consistent, but all the other theories are also consistent with what we observe. And if there's ever an observation that isn't consistent with the theory, you can just change the theory and make it fit. That's exactly why I say it's not really a proper scientific theory. You can always make it fit to whatever you measure.
Yeah, and that's a critique for all of science. That's especially in the psychological sciences and social sciences. That happens all the time. And you point out that in physics, this is an issue as well. But are you requiring that a theory to be scientific has to be observable or experimentally provable in terms of today's world? That would require that the conditions today were the conditions in the initial conditions? That seems like its own limitation.
Well, no, I'm just saying you shouldn't make it unnecessarily complicated. Like we have a pretty good theory for the universe, which is called the concordance model of cosmology, or lambda CDM. And everything else, you tap onto this. All stories that you invent for what happened earlier are really unnecessary to explain anything that we can presently observe. Now, you're certainly right that cosmology isn't done. We're getting more data, and there'll be more to explain, and those theories will become a little bit better. But I think there's a fundamental limit to what we can possibly explain with science, and it comes out of this particular structure of our theories.
Yeah, look, I think that's a very legitimate point, and you've made that more obvious than most, and I think it's an important contribution to thinking, and you're not arguing that we should stop, but we should be very careful about differentiating between what we know and what we think we know and what we can prove. And that's, of course, the nature of science. Then you go on to talk about math. You have one chapter with one of your other voices, Tim Palmer. And throughout the book, you deal with the question of is math all there is in different parts of the book. And it seems to me, this may be a little unfair, but, we can have some fun with it, that you equate, in essence, the existence of Platonism, where all math is real in a very fundamental sense, with, say, the existence of God, in that science cannot say anything about either one.
Well, I'm not equating God with maths. I'm just saying that from a logical perspective, it's a similar argument. Like if you postulate that God exists, that's similar to saying like all of maths exists, but in neither case can I actually observe it. Like there's no way I can possibly falsify it. I wouldn't really say that Platonism is a religion. I would say it's a philosophical stance. But in any case, it's certainly not a scientific conclusion that you can draw from any kind of observation.
I like the fact that when you interview people, the first question you ask is, "Are you religious?" And I think that's a very probative question, and I'm going to learn from you. So when I start talking to some people, the first question I'm going to ask them. So I know the answer, but I want to ask you: are you religious?
No, I'm not religious. The reason I'm asking this question is that I've asked a lot of physicists about this, and normally their answer is no. But, and then there comes the interesting part.
So do you have a but?
Oh yeah, the but is my book, basically. So there are a lot of things that we have found in the foundations of physics that I think have a spiritual value, which is very close to religion, but not with the overhead of having to believe in a god or something. And I think you find this in some of the answers that people give me when they're like, okay, I'm not religious, but I believe there's more to it, basically.
And I think this is a fundamental point. You deal this later in the book with what's the purpose of anything anyway. Let me jump to that, because I like to contrast two views of two of my most favorite people in the world. Steven Weinberg, who, of course, recently died, a great loss, but wonderful contribution. But his famous comment was, the more the universe seems comprehensible, the more it also seems pointless. So in your view, if you have to weigh, is the universe pointless, as Weinberg said, with is the universe about something that, for example, Paul Davies says, that the universe is about something. On that scale of pointless to about something, where does Sabine fall?
I think I'm on the middle, leaning to it's pointless, though I would say it's up to us to create a point for our own life. And I get to this at the end of the book where I say, well, we're all part of this universe, so let's try to make something out of it. And for me personally, the point of life, if you want to put it this way, of my own life, is trying to communicate what we have learned about the universe.
Yeah, and that's entirely legitimate and worthwhile, and we all have families and do the best we can in our lives, of course. But I think that's a little cheating, that if you really believe as you do, I think Weinberg's position is more honest and direct. And the thing I liked about Stephen was that he felt very bad about it. I mean, there are some atheists who feel good about it, but he felt very bad about it. But he was, he was very vigorous and intense of meeting the reality, and that reality of what it is really all about was its own energizing thought. And I felt very comfortable in that area. What I'm uncomfortable with is when physicists try to eliminate or show the falsity or the waste of time of religion. They try to substitute something, and that itself looks very false.
So I'm not really trying to substitute religion. I'm just saying there's something in between to some extent, where physicists are trying to answer some of those big questions, and they're actually getting a little bit closer. So we learn something. And coming back to Weinberg, I think one of the differences between my perspective and Weinberg's is that I think he was very much a reductionist in the sense that everything is made of small particles and the laws for the small particles are pretty much the end of it, right? He wanted to get to this final theory. In his book, Dreams of the Final Theory, he's very clear about this. Whereas I think what's missing in our theories are the big connections that hold the entire universe together. So it's kind of at the exact opposite end. I don't think that the big mysteries that we have left to solve are on the tiny scales, but they're on the large scales. They concern how we are embedded in this entire universe.
So this brings up a major point of your book, which I really do want to focus on, which is the concept of reductionism and how you deal with it. You call yourself a reductionist, but not a hard reductionist. And to me, I'm not sure how you can be a reductionist without being a hard reductionist. But you have a way, as you always do.
Well, yeah, so what I'm trying to say is that reductionism is not a philosophy. Like, I've met a lot of people who are like, but it's just a philosophy, right? But it's just a fact of nature that we can describe the behavior of large objects from the behavior of their constituents. We know this to be true. And this is also, of course, what Steven Weinberg explained in his book. But there's the question, like, if we continue to look closer and closer into the structure of matter, will it continue to be the case? And at this point, I'm like, well, we don't really know. And actually, when we think about stuff like the measurement problem in quantum mechanics, and also the issues that we have with observers in cosmology, like when we're talking about the entire universe, then maybe what our problems are trying to tell us is that this ontological reductionism has just reached its limits. So maybe we should not try to figure out if elementary particles are made of strings. Maybe our problems is describing how big objects come about.
Well, this brings up, I think, a very fundamental point of physics. I think we should continue to look for smaller and smaller, and hopefully it's not turtles all the way down, as they say. I think that's a legitimate quest, but the point you bring up is extremely fundamental, and that is, are there ontologically fundamental laws that exist in larger constituents that are not reduced, as we would say, to the actions of small particles? And I think the way to phrase this question is the question which I think you reject: is there such a thing as strong emergence? And strong emergence I would define as, in principle, not being able to explain some regularity or some law at a certain level, not being able to explain that in terms of the smaller particles, the smaller stuff of which it is made of. So that's strong emergence, where in principle you never can do it. Weak emergence, for example, why water is wet, is an emergent property of the relationship between hydrogen and oxygen and the bonding and the angles, and you can, when you see the two gases, you can't imagine how this thing could be wet, and so therefore it looks like emergence. But when you understand the physical chemistry of it, you can explain it. So I call that weak emergence. But strong emergence is in principle where you never can do that. So I think, do you reject strong emergence?
Well, I reject it because we don't know any examples. Like we've never seen any case of actual strong emergence. But I don't think you need strong emergence to have fundamental laws at large distances. And this comes out, I think, very nicely in the interview I did with David Deutsch, which was really fun. So he points out that in a fundamental theory, you might have principles that concern the universe as a whole. And his favorite example is energy conservation. Now, normally we think of energy conservation as something that we derive from the underlying microscopic theory. But you can take a different perspective and say, let's take it as something that we start from. So now we're starting with something at a macroscopic, at a large level, the entire universe, if you want to put it this way. And I think what this example tells us is that you don't have to disagree with the existence of natural laws on a microscopic scale from which you could derive the macroscopic laws to have useful macroscopic laws where the emphasis is on useful. The point is that you may have a law that you derive from your underlying microscopic reality, but it becomes very, very complicated on macroscopic scales. And then you would say, well, we instead take a different formulation of this, which is much simpler, but now you have expressed it in non-reductionist terms. So the point is that on those macroscopic terms, the useful theory might be one which does not use the microscopic information.
Yeah, to me that's a little hard to process because they're in the macroscopic. There's no extra. Sometimes you call it fairy dust. I think there's nothing extra in there other than the constituents of the micro. But yet you're saying that there's some property that the macro has which cannot be ultimately explained in terms of the micro, because that's strong emergence. I'm not sure I understand.
No, you could explain it in terms of the microscopic constituents, but it may not be a useful description. So you have your microscopic description, and now imagine you're able to do your derivation of the macro level. So this is weak emergence. But now you have a theory which is completely useless. It's just too difficult. And so you reformulate it in other assumptions.
Okay.
And those assumptions use ingredients from the macroscopic level. And they no longer rely on the underlying microscopic structures. So there's no disagreement. I think the other example that David Deutsch used is the existence of a universal computer, and that's not something which you can express in laws of the microscopic constituents, elementary particles or something. It's a property that comes out at the macro level. And it doesn't disagree with the existence of laws on the microscopic scale. And if you were really, really good, maybe you could start with something like string theory and then prove that it would give rise to a universal computer. But it doesn't really make a lot of practical sense to try to use this kind of calculation. So you would use a theory on the macroscopic level that postulates, well, universal computers exist, and that's something that you can work with.
Yeah, I think that's entirely right. I mean, we're dealing with practicality is a very different kind of question than an in principle question. There is a very distinct difference between making an argument from the practicality, what we can do. In other words, to use macroscopic principles in order to be practical, in order to understand things, from the deep ontological question. In principle, could you do it? And in principle you can, but in practicality you cannot. So that's the distinction being made.
Yes, partly. I think it's a little bit stronger because you have to keep in mind that for theory to actually be scientific, you have to be able to make a prediction with it. So if you have a chaotic theory, you might be able to make approximate or average predictions with it. If you have a theory by help of which you can't make any predictions, I would say that just isn't scientific.
Okay, that's fair. Let's deal with some other topics. Is it correct that you don't trust the second law of thermodynamics? That to most physicists is like the holy of the holies.
Yeah, that's right. So, I mean, of course, it's a good law in the sense that we can apply it, right, in thermodynamics for applications and so on. It's working just fine. But I think if you're talking about the entire universe, including gravity and quantum mechanics and all that kind of stuff, it isn't any good. And the reason I'm saying this is that ultimately this notion of entropy, which is so central to the second law of thermodynamics, derives from our perspective of what matters. To even be able to define what we mean by entropy, you have to say, what do I consider a macroscopic state, of which I count all those microstates? And I think that's really subjective, and it's based on our own perspective of the world, which may not have any fundamental meaning.
Okay, I mean, look, I think that's a very controversial position, but I think an important one, because when you challenge fundamental concepts, when you challenge current belief and what people think is fundamental, I think that's a major advancement in terms of how we think, forcing us to reevaluate what we had assumed to be foundational truth. So I am all for that. The chapter that you have, Are You Just a Bag of Atoms, leads to a lot of things. Of course, reductionism and strong and weak emergence are part of it. One of the things that you talk about is the difference between ontological reductionism and theory reductionism. Can you articulate that? Because I think that's a very probative idea.
Yes, so ontological reductionism is about the property of nature that we explain the behavior of macroscopic things by the behavior of their constituents on smaller scales. So in a sense, you find better explanations by looking at shorter scales. Whereas theory reductionism just means you can derive one theory, say thermodynamics, since we were just talking about this, from an underlying more fundamental theory, like one about the motions of atoms. This is a typical example. Now, it just so happens that historically, these two have gone hand in hand. Like if you think about how we discovered the periodic table and then the structures of atoms and the constituents of the atomic nucleus and then their constituents and so on and so forth. So we have ontological reductionism going hand in hand with theory reductionism. And the question is, like, will this continue to be the case? Like, should we look for the next better theory on shorter scales? And I think the answer is not necessarily yes, put it this way.
Or it's not necessarily the only thing that we should do, or the only thing that we should make as absolute priority. I think that would be a fair thing that you make the point. I don't think to stop fundamental physics and particle physics, but rather to see that there may be other ways to approach the so-called theory of everything, or to really have a comprehensive theory. I think that's legitimate. One thing we haven't talked about that is throughout your book that is very relevant for the Are We a Bag of Atoms, and it also deals with when you interviewed Roger Penrose on consciousness, is the big C word, consciousness. We've avoided that so far, but we can't avoid it on a permanent basis. So you have, let's see if I have one of your quotes here. You say one of the old explanations is the idea that consciousness requires more than the interaction of many particles, some kind of magic fairy dust. And so you dismiss all the concerns about consciousness pretty abruptly by lumping it all together, the panpsychists, the integrated information theory, everybody together is basically fairy dust, and that you look for a what seems to be a very robust reductionism in the approach to consciousness. Even though we don't know it today, in principle, it's obvious that it will occur. Is that a fair characterization of what you believe?
Partly. I think you make my opinion of integrated information theory sound more negative than it is. I think it's actually a reductionist approach. Like, you're trying to find an integrated quantity that you can calculate from the structure of the brain, right? So it's something that you could, in a certain sense, deduce from the physical properties of the connections in the brain. Like, if you could actually calculate this phi, which is a different matter entirely. I just think it's too simple. I find it hard to believe that something which is arguably complicated, human consciousness, can possibly be captured by a single number, basically. That doesn't really make sense to me. I think there's more to the structure of the brain.
Well, let's talk about your approach to consciousness in general. It is a reductionist approach to consciousness. Do you believe there are fundamental laws that are existing at higher levels which are needed to explain consciousness, which could not be explained by motions and forces at lower levels?
I wouldn't really say I have an approach to consciousness. I would just say that for all we currently know, we don't need anything beyond knowing what the structure of the brain is and how it interacts, and so on and so forth. I find this kind of magical thinking, like there has to be something else which makes some things conscious and others not, just unnecessary. And I think that as research continues, as neurologists figure out more about which parts of the brain are involved in what, this take will just fade away, because we'll be able to describe just exactly what are the properties that a system needs to have to be conscious.
And the general view in the philosophical community, which we can discuss, is quite the opposite, that the more we've learned about the brain in terms of how it works, the more we see the detailed structure of how the visual system works, how emotions work, etc., but the less confidence we have that we can describe the phenomenology of inner experience, the inner movie, or whatever you want, however you want to describe it, in terms of any kind of physical theory, because any kind of physical theory that you can imagine at all is some kind of an identity theory, and saying like that, whatever that is. I think you had a good thing if you kicked your toe and you had this sense that, this is going to hurt in about a second or two, because there's a difference in terms of the rate at which the nerve impulses are carried, the pain impulses, by the first touch. And so we've all had that experience. That in a second I'm going to really hurt, but I don't hurt for this second. And so those are the things we can understand, but in terms of how it happened. But how is that, those action potentials along those axons, how does those sodium and ions and passing, how is that the phenomenology of inner experience? I mean, that's the fundamental question, which has led to the growth of panpsychism as a solution. Some have gone to idealism, and then, of course, we have traditional dualism. And all of those factors have been at least becoming stronger in the philosophical community over the same period of time when the neuroscience has been dramatically increasing.
If you're asking, can I explain it? The answer is no. But I don't think that to explain it, we need anything physical beyond what we already know. I think it's really a matter of just figuring out exactly what are the connectivities that give rise to consciousness, and it'll take a long time. I'm not sure I'll see it in my lifetime. But if you're asking like what makes this experience of my toe hurting or that kind of thing, well, it's some kind of brain pattern, and all the difficulty is in some kind.
I agree, but when that is determined, when you have that brain pattern, the question is, why is that sequence associated with a phenomenological experience as opposed to just creating a behavioral experience? There is supposedly an unbridgeable gap between a behavioral response and a phenomenological experience.
Well, I agree that they're not the same thing, but I don't think there's an unbridgeable gap. I would just say, well, this pattern in my brain, that is the experience. I don't think that you need anything else beyond that.
And you find no difficulty with the aboutness and the content level of the experience, and then whatever the physical determinants at the micro level, flows of ions creating spikes of electrical activity, several on a millisecond basis. I mean, you're explaining one in terms of the other, and you have no problem with that.
No, I have no problem with that.
Okay, good. Well, that's a position, and we should check back together every 10 years or so and see if that how we're making progress on it. This is a natural place to talk about your approach to free will, because you take a very strong view on free will that basically we don't have it, and you have a great way of presenting it, because you go through all the philosophical arguments, compatibilism and libertarianism, and you have this refrain that says, but the future is still fixed, except for occasional quantum events that we cannot influence. In other words, if you want to call that, whatever that is, free will, compatibilism, libertarian, or whatever, you can do it, but the future is still fixed, deterministic, except for this little exception. And you have that phrase like an opera chorus when each of the free will stories are presented. So I really like that. I may not agree with it, but I love it.
Yeah, I did this because the issue when you're talking about free will, which I've done many, many times with different people, is you always run into this problem. What do we actually mean by free will? Like there don't seem to be any two people who mean exactly the same thing with it. And this is why I said, let's just phrase the problem without even talking about free will. So this is what we know about the laws of nature, and this is how it goes with the deterministic time evolution, and there's quantum mechanics, which brings in this random element. And this is how much we know. And then you have this problem that there isn't any meaningful way to even say that you choose some kind of future. It doesn't really make any sense. At least that's my perspective. Therefore, I would say the easiest conclusion to draw is, let's just get over with free will. It doesn't make any sense. Let's not talk about it. But of course, there are lots of people who have made a big effort trying to find a notion of free will that makes sense. And I don't a priori have a big problem with it. In the end, it's just a matter of definition. But as you say, the future is still fixed, except for the occasional quantum event.
Yeah, and that's, as I said, you have this great refrain that comes up again, or all of these, and I think that's a very legitimate thing to do. I've always felt compatibilism is an idea, and we can apply it to moral responsibility and a whole different things. But ultimately, compatibilism is really not the free will that most people think. Now, and we traditionally call that libertarian free will. And you're very strong about that. I think you said in the book that you won't even discuss libertarian free will because it's incompatible with what we know about nature. So you are obviously prioritizing, privileging what we know about nature more than the internal sense of free will, which could be an illusion or whatever else. But you have it's out of the question to even address libertarian free will that we can do other than what the past has determined in some sense, because of this privileging of the underlying laws of physics.
Well, I wouldn't go so far to say it's out of the question, but I think you don't really learn anything from it. And I list a few examples earlier in my book where we have just figured out that our human perception of how things happen, like when it comes to the notion of time, for example, isn't particularly reliable. So that we have an experience of something like free will, I don't think is a strong argument against all the evidence that we have collected that special relativity and quantum mechanics are very accurate descriptions of nature.
Some would argue, of course, the opposite, that the thing that we know most surely is our libertarian sense of free will, and that if that somehow conflicts with what we currently know about physics, maybe we should look at what we currently know about physics and challenge that, as opposed to the other way around.
So do you actually think that this would get us anywhere?
I'm not sure that's the ultimate question to ask, because if the answer is no, it won't get us anywhere, does that make it illegitimate? It may be that the universe is so structured that it won't get us anywhere, but that's the way things are in some sense.
Well, to me, this would be pretty much like giving up on science, right? I mean, to begin with, if you really want to hold a position like this, you would actually have to argue that in some sense, the human brain is not really made out of particles, because we know what particles do if you put them together, right? They still behave according to the laws of the standard model of particle physics and quantum mechanics and general relativity and so on. So you have to put in, as I phrased it in the introduction, some kind of magic fairy dust to make the thing work. And I think that's pretty much throwing out science altogether. You know, it's just saying I'm allowed to add something that isn't actually necessary to explain anything that we observe, just because I don't like to accept that nature is the way that our observations tell us.
Giulio Tononi, Christoph Koch, and some others, as promoters of integrated information theory, have a recent paper in which they claim that if you buy into integrated information theory, that you can come up with what is effectively a libertarian free will. They don't use the term libertarian because of its historical philosophical baggage, but they say that with IIT, we have true alternatives. We make true decisions, and we, not our neurons and not our atoms, are the true cause of our willed actions and bear true responsibilities for them. It's very controversial, but it's a very aggressive position that free will, in the libertarian sense, I'll use the term, they don't, is real, and and their argument hinges on what they call the proper understanding of consciousness as true existence, as captured by its intrinsic powers ontology. And they say what truly exists in physical terms are intrinsic entities, and only what truly exists can cause. So if you're going to have mental causation, you have to have true entities, and IIT says consciousness is such.
No, I haven't seen the paper, but I mean, there are similar arguments. It's usually a play on what you mean by causation. You know, what's the thing that causes what other thing? I don't think, I have a hard time seeing how this would give you a libertarian free will, because it would still have to be compatible with this underlying theory. But this is the entire problem with the argument from the excluded cause. So if you already have an underlying theory, like the standard model of particle physics, for example, then whatever this overarching theory is, and it may be integrated information theory or something else that you can come up with. As I said, I think integrated information theory is too simple. It'll still have to be compatible with it. It can't possibly disagree with it. Or if you want to go so far to say it actually disagrees with it, well, then you should make a prediction, and then I want to see evidence for it. So I don't think that any argument of this, however you want to redefine cause or causation or your emergent property or whatever doesn't make this fundamental structure go away.
Here's a test question that I ask myself, and I like to ask in terms of different theories of consciousness. And it's this. Is it possible, in principle, for our first-person sense of consciousness to be uploaded in some medium in what's called virtual immortality? We certainly can do it in a way that it will seem that, and the same as approach to AI, artificial intelligence, is that conscious. It would seem by any test in communication it was conscious, but is it really conscious is a first-person experience that is difficult to see how that can ever be discerned. But the question is, in principle, do you believe in your approach to consciousness that it is ever possible for that first-person sense of consciousness to be transferred to another medium?
Yes, though I'm not sure you can do it with presently existing computers. So that's a different question.
Go 1 billion years into the future and assume the human race survives and science increases. However long you want. In principle, can you do that?
Yeah, I would say yes. And I would actually say that if you look at integrated information theory, it doesn't really tell you much about the physical substrate that you actually use. It's a theory about the properties of the connectivity of the thing in a vague sense. So if you have something with particular properties, you take the properties, you upload them to a different substrate. It should be the same sense of consciousness.
I believe what you just stated is completely internally consistent. That if one believes that there's no fairy dust of any kind, whether it's panpsychism or dualism or soul, whatever, if there's nothing like that, then you have to conclude that you will be able to do that, because otherwise it's not logical. A lot of people don't do that. They want consciousness to be purely physical, but doubt you could ever do that. And I think that is inconsistent. We're very, very far away, if that were ever possible, from doing it. But if you believe that there's no fairy dust, you have to conclude that first-person consciousness with the same internal experiences will be able to do that. Of course, that brings up a whole other set of questions. If you can do it once, you can do it twice, and if you could do it twice, you could do it an infinite number of times. And so what then happens to your first-person consciousness in that case? That's a question, we could spend the next hour on and not make any progress, I'm sure.
Yeah, it brings you to this transmitter problem. Like this is the way that I phrase it, right? So if Kirk goes through the transmitter and you send him elsewhere, but you don't destroy the original, now you have two Kirks. What happened with his consciousness, right? So it's this question, and it's a difficult question that I think you can't answer with what we currently know about the laws of nature. I mean, there is this issue that you can't copy a quantum state, which kind of seems to answer the question, but it assumes that consciousness has this very strong quantum behavior, which is very, very controversial in itself.
Right.
So we don't really know.
Good. I'm with you on that. You have a chapter, Was the Universe Made for Us?, which deals with the fine-tuning argument that some people would use to prove or demonstrate that there's a supernatural being, whether it's God or some type of simulation going on. You equate, and this is what I find fascinating, the fine-tuning argument for God or for simulation with the multiverse and with its anthropic principal selection process. So you put both of them in the same category as ascientific. And so I want to understand then, how do you deal with the so-called fine-tuning argument? And you do it by comparing different ways we're approaching what fine-tuning means in a probabilistic sense.
Yeah, right. So the reason I'm lumping them together basically is that physicists have come up with both for the same reason. We have those fundamental laws of nature, like the standard model of particle physics, with all those parameters like the masses and the coupling constants and that kind of stuff, and general relativity. concordance model, and we want to know why those constants are what they are. And now the fine-tuning people basically say, well, it can't possibly be coincidence, because if you change this constant a little bit, then, I don't know, carbon wouldn't come into existence, or complex chemical structures couldn't form, and that kind of thing. Therefore, there has to be a God, to make a long story short. Whereas the multiverse people say, well, the explanation is that all the possible values of those constants exist in this larger thing that we call the multiverse, where all possible combinations could exist somewhere. But they're both motivated by the same thing. They want an explanation for the values of those constants. And I think in both cases, the problem is the same, which is that this supposed explanation is unnecessarily complicated. That doesn't necessarily mean it's wrong, but it means it's not scientific, which is why I say it's ascientific.
Okay, so can you make progress from your perspective? Do you have to assume that there's this different probabilities, if we're looking at priors in a Bayesian sense, or looking at probabilities in a distribution sense? Because if you have a universe that's infinite and you're picking out one set of values that you think is very rare, but you don't know what the total set is, you really can't do that. So you're kind of arguing that the fine-tuning argument is not even an argument, because we don't really know if it's fine-tuned, because we don't know, and maybe we can't know in principle, what the universe of possibilities are in order to say that this set is fine-tuned.
Exactly. So the problem is, if you say, like, those particular constants of nature, they're very unlikely. What do you mean by this? Like, you have to quantify it somehow. And we can't quantify it because we can't measure what's the probability of getting this particular collection of constants. And then you can make up some complicated story about it, like with the probability distribution over the multiverse and so on and so forth. And as I said, this isn't wrong, but you don't need it. Like, for practical purposes, what you need are the values of those constants. Now, you ask, can we make progress with this? I'm not sure exactly what you're asking for, but it's certainly possible that even leaving aside all the fine-tuning arguments and the multiverse, one day we'll be able to calculate at least some of those constants from a better underlying theory. I consider this to be totally possible.
Okay, and that's one of the challenges, and that's sort of the necessity argument, that the constants of nature, which look like they're fine-tuned, are necessary in the sense that it had to be this way by some underlying principle. It's the only way that it could result. Many people would like to do that, but it seems that from quantum mechanics and the different and string theory, various other things, there seems to be such a range of possibilities that one underlying theory seems less likely today than it would have been even several decades ago. That doesn't mean it won't be done, but it seems to be less likely today that you can derive the constants from one single underlying theory, so that it could only be that way, which would answer the question. That's clear. But I want to still go back to your probability analysis, because it's entirely right, I believe, from a standpoint of assessing whether the constants are indeed fine-tuned. It's a very coherent argument that says we can't know that. But I want to take it to the next step. And so supposedly we could know that. I want to give you a counterfactual. If you believe that we could know that because we really did have a way of assessing the likelihood of this set of constants of nature in the overall set. So if you believe that as a counterfactual, how would you then proceed? Would you say that therefore the credence of a multiverse, or the credence of some sort of a supernatural or outside the universe, outside our universe, a creator of some kind, is more likely?
So I guess I wouldn't go so far to say, to speak of a creator, because I'm not exactly sure, like, scientifically, how would he even formalize this. But I think it'd certainly be the case, given that we somehow knew the distribution over the multiverse, and it turned out that the likelihood of getting a universe such as ours is very, very small. That would certainly be something where I would agree it requires an explanation, because that's exactly what we do in science, right? If we have something that has a very small probability of happening coincidentally, then we say, well, there has to be an explanation for it. And in this case, I would agree. And I also think that this is where people who make this argument come from, right?
Exactly. And I think that's a fair comment. And once again, I'd like to check back with you every decade or so. So we'll see if we're making any progress on this. Let me ask you what is a closer to truth favorite big question, which I don't think you address in the book, probably because it'll be ascientific. But why is there anything at all, including the laws of physics? Why is there something rather than nothing?
I don't know. This is why I don't discuss it. I do touch on it a little bit when I talk about the question, will we ever have a theory of everything, like one that actually can explain it all? And the answer I propose is no, because whatever this theory is, it can't explain why it is the one. So that there'll always be another question. Like the universe has to be some way and not another. How do you explain it? I think you just can't. And the question, like, why is there something and not nothing, has to be the same flavor, right? We observe that the universe is one way and not another. There is something and not nothing. But why? I don't know.
Fair. I would say I don't know either, but I like to luxuriate in the question and look at it from many, many different points of view. And what do you mean by nothing? And of course, many physicists have a very rich sense of nothing, quantum foam and quantum tunneling and all these very complicated things that are part of their nothing. But that's not real nothing. It's very difficult to get to a real nothing. As I said, I'd like to luxuriate in that, but certainly I would agree it's ascientific. That brings up, kind of an overarching question, Sabine. All of your big questions naturally are the kinds which are addressable by science, and when they're not, you label them very aggressively ascientific. But are there any then big questions that science in principle cannot address, much less answer?
Well, yeah. So I would say one thing that science can't address is the question, why does science work at all? Like this is not a question you can answer with the scientific method. Why does the scientific method work? Right? We know it does work. We can observe this, and this is why we use it. But fundamentally, I think we don't know why. And I can't think of any way you could possibly answer this question with science.
Does that mean if you cannot answer or even address a question with science, does that invalidate the question, or it's still a real question and it then becomes a demarcation of science where science ends?
Well, yeah, for one thing, I may just be wrong. God knows, maybe someone smarter than I will find an answer to the question. But at least I can't think of a way to do it. It's a perfectly legitimate question. I don't think that the only legitimate questions are scientific questions. So this particular one I would put into the realm of philosophy. And I think philosophy is a very important discipline, and it'll continue to be important.
Sabine, I've thoroughly enjoyed our conversation. I wish we can go on forever, but I really mean it. Every decade or so for the next 1,000 years, you and I are going to get together and do a benchmarking of where we are. Thanks, everyone, for listening. You can watch many more of Sabine's videos on closertotruth.com, and, of course, many, many more on her YouTube channel, Science Without the Gobbledygook. So, Sabine, great to see you. Good luck with the book, Existential Physics. I really enjoyed reading it. One of my favorite books recently. So thanks again.
Thank you so much.
Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing.